Hello everybody. In this video we are going to be looking at the solutions to the college prep reflection and mirrors homework problems 16 through 20. Let's get started with problem 16. An object is located 20 centimeters in front of a convex mirror with a negative 15.0 centimeter focal length. Find the image position using both a scale diagram and the mirror. So the first way they want us to find the image position is by just using a ray diagram and drawing our rays. As you guys should know by now that we know how to draw three rays, and once they intersect, or we see where the reflected rays intersect, that will tell us where the image is located. So let's do that first. We'll look at our ray diagram. So here is our ray diagram for a concave mirror, or a convex mirror, sorry. So here we have our object right here. And our first ray, which I'm going to highlight in red, my incident ray is parallel with the principal axis. So you can see that the incident ray here is parallel with my principal axis. When it strikes the mirror, it's going to reflect off of the mirror at an angle so that the reflected ray is lined up with the focal length. If I trace the reflected ray back behind the mirror, remember the ray of light doesn't go through the mirror, it reflects off of the mirror, but if I take that reflected ray and I just trace it back behind the mirror, it's going to line up with the focal point. My second ray, which I have in this whatever weird greenish color there, my second ray, the incident ray, is lined up with the focal point. So my incident ray goes from the tip of my arrow, which is my object, to the mirror so that it is lined up with the focal point behind the mirror. When that ray reflects off of the mirror, the reflected ray is going to be parallel with the principal axis. So in the second ray, incident ray is lined up with the focal point, reflected ray is parallel with the principal axis. And again, if I take this second ray and I trace the reflected ray back behind the mirror, I can see where it intersects with the reflected ray from my first ray. My third ray that I can draw is if I line my incident ray up with the center of curvature. So my incident ray from the tip of the arrow is lined up with the center of curvature. When it strikes the mirror, it's going to strike the mirror at an angle of 90 degrees, and according to my law of reflection, it's going to reflect back on itself. So once again, if I trace this ray back behind the mirror towards the center of curvature, I can see that it intersects with the other two reflected rays. And that point where all three of these rays intersect is where my image is located. So my image is right there. And remember, because all of my incident rays came off the tip of the arrow, where they intersect is the tip of the image. Now let's take a look and see how we can do this mathematically. We know that our object distance is 20 centimeters. I know my focal length is negative 15 centimeters. And remember, it is negative because the focal point is behind the mirror. And the image distance is what we are looking for. So using my mirror equation, I need to solve for the image distance. So I want to get that by itself on one side of the equal sign. So I'm going to subtract 1 over the object distance from both sides. When I do that, I will have 1 over the image distance equals 1 over the focal length minus 1 over the object distance. Now I want to simplify what is on the right side of the equation here. So when I simplify that down, I use my lowest common denominator, which is going to be the object distance times the focal length. And when I do that, I'm going to have the object distance minus the focal length divided by the object distance times the focal length. Now remember, my unknown is still in the denominator of the fraction, so I can't solve for it yet. So I am going to rearrange this formula to solve, or to move that up into the numerator. And essentially all I have to do is flip both, or the fractions on both sides of my equal sign. And when I do that, I will end up with my final equation. And I can plug my known values into that equation, and when I do, I am going to have an image distance of negative 8.57 centimeters. A couple of things to note about that. First of all, note that my image distance is negative because the image is located behind the mirror. The image is closer to the mirror than the object is, so the image distance is also less than my object distance. The object is 20 centimeters away from the mirror, and the image is a little bit over 8.5 centimeters away from the mirror. Problem 17. A convex mirror has a focal length of negative 13.0 centimeters. A light bulb with a diameter of 6.0 centimeters is placed 60.0 centimeters from the mirror. What is the light bulb's image position and diameter? So we are going to solve this one mathematically, much the same way we did the previous problem. In this case, we are given the focal length, which is negative 13.0 centimeters. And because it is a convex mirror, I know that the focal point is behind the mirror, which will give me a negative focal length. The height of the object is 6.0 centimeters, and the distance of the object from the mirror is 60.0 centimeters. We are looking for the image distance and the image height. So to find the image distance, if I have the focal length and the object distance, again, I'm going to start with my mirror equation, and I'm going to rearrange it just like I did in the previous problem so that I have solved for the image distance, which will give me this version of the formula right there. Then I could plug my known variables into the equation, and when I do that, I am going to have an image distance of negative 10.7 centimeters. Now to solve for the image height. I know the object height and I know the object distance and the image distance, so I can use this form of my mirror equation. Solving that for the image height will give me the image height equals the negative of the image distance times the object height divided by the object distance. Plugging my known values into that formula will give me an image height of 1.07 centimeters, or rounded to two significant figures, 1.1 centimeters. Problem number 18. A convex mirror is needed to produce an image that is 3/4 the size of an object and located 24 centimeters behind the mirror. What focal length should be specified? So the magnification we need is going to be 0.75 or 3/4. That's my magnification. It's a convex mirror, so I know that the image distance is going to be negative 24 centimeters. That's telling me that it's 24 centimeters behind the mirror. So that will be a negative 24 centimeters, and we are being asked to find the focal length. So to find the focal length, I have the image distance, but I still need the object distance in order to find the focal length. And I can find the object distance using my magnification equation. So I know that the magnification equals the negative of the image distance divided by the object distance. Solving that for the object distance will give me the object distance equals the negative of the image distance divided by the magnification. So negative 24 centimeters divided, or the negative of negative 24 centimeters divided by 0.75 is going to give me an object distance of 32 centimeters. Now I can use my mirror equation. Don't need to rearrange it. I just need to solve for the focal length, which means just getting the focal length from the denominator into the numerator. And when I do that, I'm going to have the focal length is equal to the image distance times the object distance divided by the object distance plus the image distance. Plugging all of my known variables for the image distance and object distance into that equation will give me a focal length for this mirror of negative 96 centimeters. Number 19. A 7.6 centimeter diameter ball is located 22.0 centimeters from a convex mirror with a radius of curvature of 60.0 centimeters. What are the ball's image position and diameter? So we have the height of the object, which is 7.6 centimeters. We know how far the object is from our mirror, and that is 22 centimeters. And we know the radius of curvature of the mirror is 60 centimeters. And it is negative because it is a convex mirror. We are looking for the image height and the image distance, or the image distance and image height, really, in that order. So let's do the image distance first. We are going to need to find the focal length from the radius of curvature, and I know that the focal length is half of the radius of curvature, so negative 60 centimeters divided by 2 will give me a focal length of 30, or I should say negative 30 centimeters. Now I can use my mirror equation, and solving that for the image distance, as we have done before, will give me the image distance equals the object distance times the focal length divided by the object distance minus the focal length. I insert my values for object distance and focal length into that equation, and that will give me an image distance of negative 12.7 centimeters. Now to find the image height, I know that I'm going to use this form of my magnification equation. Solving that for the image height will give me the image height equals the negative of the image distance times the object height divided by the object distance. Again, plugging all of my known variables into that equation will give me an image height of 4.4 centimeters. Problem 20. A 1.8 meter tall girl stands 2.4 meters from a store's security mirror. Her image appears to be 0.36 meters tall. What is the focal length of the mirror? We are given the object height, which is 1.8 meters. We are given the object distance, 2.4 meters. And the image height, 0.36 meters. And we are looking for the focal length. So in order to find the focal length, I know I'm going to need both the image distance and the object distance. I have my object distance, but not my image distance. However, I do have the object height and the image height, so that together with the object distance, I can use my magnification equation to then find the image distance. So again, taking my magnification equation, solving that for image distance will give me the image distance equals the negative of the object distance times the image height divided by the object height. Plugging all of my known variables into that equation, that will give me an image distance of negative 0.48 meters. Now I can use my mirror equation to solve for the focal length. And remember, I do need to get my focal length out of the denominator and into the numerator. I can't solve this as long as my focal length is in the denominator of that fraction. So when I do that, I am going to have the focal length equals the image distance times the object distance divided by the object distance plus the image distance. Plugging my known variables into that equation, I will have a focal length of negative 0.60 centimeters.